Vishnu sir, can you start?
I think maybe we can start, but the participants number is around 150, sir.
80. Yes, yes.
Usually 140 to 150 will be joining.
Okay.
Maybe I think we can start the session.
Vishnu sir, can you start?
I think
I got some notification the recording has stopped.
Yes, sir. Actually, when we start only, I think Dr. Vishnu will start the recording.
Oh, okay. Maybe we can start in 3 minutes, maybe. Then we have enough participants.
Surabhi ma'am, good morning. He kept one message.
3 minutes. Then we have enough participants.
Surabhi ma'am, good morning. He kept one message.
good morning, Dr. Surbi.
Good morning.
Good morning.
Good evening from here.
Oh, for you it is good evening, yeah.
Good evening, ma'am.
Yeah.
How are you doing, Vikrant?
I'm doing well. Yeah.
Good morning, Dr. Surbi.
There's a lot of echo, I think.
Yes, sir. Yes. Ma'am, Vishnu sir, can you? I think it is a echo can.
What time is it, Surbi, for you?
It's coming up to 4:30 in the evening.
Mhm.
Yeah. It's not very late.
Okay, okay. You have shifted halfway across the world.
Yeah. Well, I shifted halfway across the world in the first place, going all the way to UK. So why not again? First time is always a new experience. Second time you do it with some experience. Dr. Vishwanath, I think we can start now. We should start on time. The participants will keep joining.
Yes, yes, we have to start now. Yes, yes, ma'am.
Okay, then let me begin then.
Please.
Yeah. So I would like to thank the organizers for giving me the opportunity, and it's also my pleasure to be here to share this presentation and some knowledge on solid oxide fuel cells and its applications in industry. So today I will give some fundamental knowledge on solid oxide fuel cells, or SOFCs in short, and what is AVL doing in it and its applications in industry. Before I jump into the presentation, for the participants, I would like to introduce the company and what AVL is. So AVL is a privately owned, biggest independent consulting company, mainly for the automotive industry. It was founded in the year 1948, and as on date, we have about 11,000 employees worldwide. And every year we invest roughly between 10 to 12% of our turnover into R&D. So in-house R&D means more novelties coming out for different technologies within AVL, and that increases the value of the company. And more than 65% of our employees are engineers and scientists. And every year we are almost in the top 2 of the number of patents granted in Austria. So how is AVL organized as a company? We have 3 major departments: engineering services, which mainly looks into how to engineer different powertrains, engines, battery systems, fuel cell systems, and many more applications. Then we have the instrumentation and test systems department. So this department is mainly focused on developing measuring instruments and test beds and other equipment needed for measuring different aspects of the technology. For example, if there is an emission measurement requirement, there is a product from AVL which can measure what kind of emission species are coming. Or for example, if you want to emulate a battery, there is also an equipment which can emulate a battery. And finally, we have the advanced simulation technologies. So this department develops software tools and techniques by which the previous two departments can use these tools and techniques to make a virtual system or a virtual product. And these tools are also available for customers to buy. Now, focusing, since this lecture is about fuel cells, I would like to share what is the fuel cell global footprint in AVL. So we started development in fuel cells in the year 2002. And so far we have established fuel cell technical centers in Graz in Austria, which is the headquarters. But besides that, we have a dedicated PEM fuel cell office in Vancouver in Canada. And we also have expertise and facilities in Kecskemét in Hungary. And we have developed a technical center in Warsaw in Poland and also Remscheid in Germany. So in total, we have about 500 engineers who are working in this technology as on date in all engineering, simulation, and testing. And we have about more than 170 granted patents in this fuel cell technology. So what is the focus for today? So today I would like to give some introduction to SOFC, the basics, fuels used, and some applications. What is AVL doing particularly in this? Since I'm from Instrumentation and Test Systems department, I would like to give the activities from the Instrumentation and Test Systems side. And finally introduce the Fuel Sum project. The Fuel Sum project is one of the EU-funded projects that we are currently working on. And this is a strategic project for AVL. So let me jump right into the SOFC basics, fuels used, and applications. So first, how or what is an SOFC and how does it work? SOFC is an acronym for solid oxide fuel cell, and it falls under the category of high temperature fuel cells. The other high temperature fuel cell from textbooks is the molten carbonate fuel cell, and the principles of operation are totally different. So what does an SOFC do? It's an electrochemical device which converts chemical energy of the fuel into electricity and high quality heat. As you see from the picture on the right side, we have a schematic which is taken from Wikipedia. So you have fuel coming in, and here you have oxidation of the fuel. And then you have electron split up, which goes around the external circuit. This could be any load which is used. And then on the other side, you have either air or pure oxygen coming in. And then the oxide ions are going across the membrane, mingling with the protons and then producing water. So what comes out is your excess fuel and water on the anode side and your air depleted of oxygen on the other cathode side. So what is the typical operating range of such a high temperature fuel cell, and why is it called high temperature? Because it operates between 600 and 1000 degrees C. So when they started solid oxide fuel cell research so many years ago, back in the 1980s, 90s, most of the solid oxide fuel cells were operating at about 1000 degrees, which is very, very high temperature. But these days, most of the companies making solid oxide fuel cell stacks, they are aiming to be somewhere between 600 and 800 degrees C. So the solid oxide fuel cell conducts oxide ions and not H+ ions, because if it conducts H+ ions, It's mainly in a PEM fuel cell with the state-of-the-art technology. And the other major difference is the water which is produced here is in vapor form or in gaseous state and not in liquid state. So now an SOFC is one single cell, and then if you put many of these cells together, you get a stack. So in this one single cell, you have 3 layers. One is the anode, or we also call it the fuel electrode. And this is mainly a mixture of nickel and YSZ. YSZ stands for yttria stabilized zirconia. So you have a matrix of these two metals put together, or an alloy. Or you can also use nickel with GDC. GDC stands for gadolinium doped ceria. So this is also another state-of-the-art material which is used in the anode. Now coming to the electrolyte, which is sandwiched in between the anode and the cathode, you have pure YSZ, which is yttria stabilized zirconia, or you have GDC, gadolinium doped ceria. And on the cathode side, where the air or the oxygen is passed through, you have an LSM YSZ. LSM is lanthanum strontium manganite, or you have LSCF, which is lanthanum strontium cobalt ferrite. So these are the state-of-the-art materials used in different layers of the cell. Of course, there are so many more materials which can cater to different needs of the cell, but those materials would want a separate lecture topic. So I will not go into that now. Interested students and faculty members can, who have strength in material science, can look into this, can look into the material aspects of solid oxide fuel cells in a separate lecture, or it's described in a separate book. Let's take a look at some basic reactions which happen in solid oxide fuel cells. So the fuel electrode or the air electrode is where the oxidation of the fuel happens, electrochemical oxidation. So if you have hydrogen as the fuel, it combines with the O2 minus ions coming from the electrolyte, and then you have water produced in the gaseous state, and you have electrons released. So the fuel, which is hydrogen, is electrochemically oxidized to generate electrons, which then pass through the external circuit. Then on the cathode side, or it's also called the air electrode side, you have cathodic reduction. So the oxygen or the air is reduced to form these O2 minus ions, and these pass through the electrolyte to go to the other side. So if you put these two reactions together, then you have H2 plus half O2 giving you H2O. So you add the half to balance out the reaction. And then it's a simple reaction where hydrogen combines with oxygen to produce water. And on the right side, you see a little more detailed 3D diagram of how this 3 layers are sandwiched together. And this part where you see the red one, that it's highlighted as TPB, it's called the triple phase boundary. This is where the electrode, electrolyte, and the gaseous fuel come into play. And this red region is where your reactions take place. So general rule of thumb is more TPBs in your electrode, more reaction which happens on the electrode. Now let's look at what happens if you use methane in the SOFC. So here in the above reaction, we use hydrogen. And now if you use methane, what happens? So normally methane, there are 2 reactions which take place. So you have the steam methane reforming. So you have methane plus H2O giving you 3H2 plus CO. So here H2 and CO is the fuel for the SOFC. And then you have the water gas shift reaction where your carbon monoxide combines again with steam to produce CO2 and H2. So in general, you have hydrogen which is produced. So 4 moles of hydrogen are produced, which is then used in the SOFC as a fuel to produce electricity and heat. And as you see, the steam methane reforming is an exothermic reaction, and the water gas shift is an endothermic reaction. So when you add these two reactions together, it is still slightly exothermic. So these are the basic reactions with 2 most common fuels used in SOFC, mainly hydrogen and methane. Before jumping into the high level part, a little more basics for the audience. So the polarization curve, I'm sure there will be more lectures on the polarization curve coming, and maybe also yesterday something was explained, but I would also like to touch upon this. So every cell which is manufactured is to be tested for the polarization curve. And why is this important? So the first line that you see, which is OCV, which is open circuit voltage. And then ideally, we would like the cell to be on this line all the while if you change the current density, because then your voltage is constant at any current density. But fundamentally, this cannot happen due to laws of physics and other science principles. And why this cannot happen? So this equation that you see here, it's called the Nernst potential. And this depends on the change in Gibbs free energy. And it also depends on a few factors on the partial pressures of the reactants. It also depends on the temperature of operation and the gas constant and all this. So just because of this fundamental reaction, you have already this flat line dropping down slightly to this line that you see here. And finally, when you calculate the actual cell voltage, which is subtracted from the Nernst potential and the losses. So these losses are categorized as activation loss, ohmic loss, and concentration loss. So what this means is activation losses are normally just to get your reactions kick-started. There is certain amount of energy needed, and to cross this energy, you have some losses. Ohmic loss just follows Ohm's law, and then higher the current density, more the ohmic losses. And concentration losses are mainly from the lack of reactants at the TPBs at the triple phase boundary or the electrode sites, where if there is no reactants, then no reaction can happen, and then there are losses. So if you add all these losses, it comes to a certain value. And then when you subtract that from the Nernst potential, you get your actual cell voltage. And that is what is this curve here. So from the ideal straight line, it drops down to something like an S-shaped curve. And higher the current density, you have more concentration polarization losses. If you operate at low current densities, you have activation polarization losses more. So this is the fundamental SOFC polarization curve, and this is how the single cells are characterized. And then you can stack them together to get a stack polarization curve if you have an SOFC stack. Let's take a brief look at the different cell and stack designs. So I mentioned earlier, we have 3 layers in a single cell. You have the anode, the cathode, and the electrolyte. So how can you make different architectures of these cells? So you can either make the electrolyte quite thick, and then you can make the anode and the cathode very thin, or you can make the anode quite thick and the other 2 layers thin, and same way with the cathode quite thick. So what is the advantage of making the electrolyte quite thick? So if you make the electrolyte quite thick, then the cell itself is quite stable, and it has got a very good support structure. But the drawback is you need very high temperature of operation, more than 850 degrees. That's why the initial SOFC research was mainly about 1000 degrees, and all the cells were electrolyte supported. So why this happens is because the ohmic losses are mainly concentrated in this portion. So you need more driving force to put your oxide ions through the electrolyte, and this causes high temperature of operation that is warranted from here. So then people thought, okay, we don't want to go to high temperature operation. What can we do to limit operation below 800 degrees? So then they came out with some novel ideas like, okay, let's make the anode thicker or the cathode thicker. And then if we make the electrolyte very thin, then the oxide ions can easily pass through and the ohmic losses will be less. So many solid oxide fuel cell companies and other research institutes focused on developing cells and materials for SOFCs. Most of them work these days with anode supported cells because this is proven to be a very good design, and it also gives quite good performance. Now, after the cell is manufactured, you need to make it into a stack because from a single cell, you only get about 0.7 volts, which is not too much. And when you're looking at applications which needs hundreds of volts, you need to put all these cells into a stack. And on the right side, you see some different stack designs. Let me go from bottom all the way to the top. So the most common stack design is the planar stack. So you have either square or rectangle cells, just stack them together, then you have a planar stack. It's not so easy just to stack them. Of course, you need to make some manifolds for the fuel and air. You need to put in between interconnects to collect the current. So all that comes in between. But you get the idea as to how the cells get stacked up. And on the top, you can also make the cell not only flat, say if you roll it up into a cylinder shape, then you get a cylindrical cell. Here, you can either pass the fuel on the outside or you can pass the fuel on the inside, depending on which side the anode and the cathode is. And then if you put many of these tubes together, you get a tubular stack. And in between that you see here is a combination between tubular and planar, which is called flat tubular. So this has got some advantages from the planar stack and also some advantages from the tubular stack. So the advantages of the planar stack is it's got high power density. And the advantage of the tubular stack is it can endure very large thermal cycles, but the power density is not too high. And the flat tubular is a combination between the two. So the road to hydrogen, everybody is talking about hydrogen economy now. Most of the countries have a hydrogen agenda in place, a hydrogen roadmap in place. So fuel cells are a technology to bridge this gap. They are not the solution, but they are a solution to bridge the gap to go from fossil fuel-based economy to a hydrogen economy. So we have PEM fuel cells here, we have SOFCs here. These are the two main fuel cells that are used in the market and also manufactured and used in different applications. So in the transition from a fossil fuel-based economy to a complete hydrogen economy, we have so many other fuels in the way, like methane, biogas, we have ammonia, methanol, and all these. Now, the good part is you can use different fuels in an SOFC, but you cannot use other than pure hydrogen in a PEMFC, because if you do that, it will kill the PEMFC immediately. So the fuel cell technology itself is lower in emissions. It's got a higher efficiency than an IC engine, and it can meet the energy growth that we need. Some of the hard to abate emission sectors like aviation, shipping, steel production, chemicals, all these are very, very hard to electrify. You cannot just use batteries in these areas. It needs a hybrid solution. And this is where fuel cells can play a very big role. Some more basic knowledge on the differences between the SOFC and the PEMFC. So the SOFC is slightly electrically efficient than the PEMFC. And if you see the open circuit voltage of a PEMFC, it's about 1.23 volts. Whereas for the SOFC, it's 1.07 volts roughly. So why is the SOFC more efficient than the PEMFC? This is the polarization curve. So we start with the flat line, and after all the losses, you subtract, you come to this S-shaped curve, which I talked about earlier. So what happens is when you go higher in temperature, all these electrochemical reactions that was shown in the previous slide, they get promoted, which means they get a bit faster. If they get a bit faster, the overpotentials, all these ones, they get a bit lower. And if they get a bit lower, then your actual cell voltage is a bit higher. And this leads to more electrical efficiency from the SOFC. So here I have put the typical graphs from the PEMFC and the SOFC. And you see here roughly for the same current density range, the SOFC has got a higher voltage on a cell level compared to the PEMFC. So that translates to a higher electrical efficiency for the SOFC. Now will be a good time to take a look at the differences between the PEM and the SOFC technology. So here, the major differences is PEM operates somewhere between 60 and 80 degrees. That is the sweet spot for the PEM technology. Whereas for the SOFC, we need somewhere between 600 and 900. I also mentioned 1000 before. The fuels used, we need pure grade 99.99% pure hydrogen for PEMFC, whereas SOFC is fuel flexible. You can use a range of fuels. Efficiency, PEM is about 50% electrically efficient on a stack level. SOFC is about 60% electrically efficient on a stack level. CHP, which stands for combined heat and power. So this is limited in PEM because the temperature range is quite low, whereas here it is possible to use the heat coming from the exhaust of the SOFC. The water which is produced is at the cathode side for the PEM, whereas for the SOFC is on the anode side or the fuel electrode side. You have platinum as a catalyst in PEM. You have nickel as a catalyst in SOFC. Nickel is cheaper than platinum. Then you need a thermal management via a dedicated coolant for the PEM fuel cell, whereas in SOFC, the complete thermal management is just by blowing air on the cathode side. The dynamic response of the PEM is excellent. So if you turn it on and off, or if you just change the load immediately, the PEM is able to respond almost instantaneously. The SOFC is not so good in terms of dynamic response. It takes time because why does it take time? Because it operates at high temperature. And since it operates at high temperature, there is thermal inertia. And thermal inertia always takes time if you change one state to another state. So some advantages of the SOFC over the PEMFC. Of course, PEM also has lots of advantages, but I'm just trying to give some perspective on the SOFC side. So fuel flexible. With the current fuel infrastructure that the world has, it can easily fit into the fuel infrastructure. It's got a higher tolerance to impurities, sulfur, carbon monoxide, CO2, etc. High electrical efficiency. Combined heat and power is possible. There is no complex water management and no expensive catalyst needed. I have put down a Venn diagram here to make it clear on what fuels get used in SOFCs for which applications. So this big blue, this big bubbles are the applications, and the fuels which are used for those applications are mentioned here. So for example, if you take a residential combined heat and power, which means a small boiler-like unit which can provide you with both electricity and heat. So here the two most common fuels are hydrogen and natural gas. Whereas if you take a generating station or a community power station or a marine application, you could use a range of fuels from liquefied natural gas or ammonia or methanol, natural gas also, and hydrogen. So you have a range of fuels. And a range extender, this was an application almost a decade ago where they wanted to have an SOFC as a range extender on the battery vehicle. And here you could still use natural gas, biogas, methanol, and ammonia, and maybe also diesel without sulfur. So the most common fuel across all the applications is natural gas, which can be used in the SOFC. Let's take a look now. Now that we have seen some basic cell designs, we have seen how an SOFC works, we have seen what are the basic reactions, what are the advantages. Let's move on to a little more high level application side. So a basic SOFC system, how does it look like? So in the middle, you have a SOFC stack, which is comprised of many single cells put together. And on the cathode side, you have a air blower or a compressor, which is then getting heated up with a heat exchanger and then blows hot air into the cathode side. On the anode side, you have hydrogen, which also has a compressor, gets heated up because you cannot blow cold hydrogen inside. So you need to heat it up to the SOFC operating temperature. You put it in, the complex reaction happens inside, produces electricity with 60% efficiency, and you have some heat which is coming out. And this heat is high quality heat, which can be used. And if you use the heat, then you have a combined heat and power efficiency of about 85% from the system. So this is a very, very simple system of how you can make an SOFC. Now let's look into a little more detailed system. So here, what generally you cannot just feed the fuel directly inside. You need maybe a steam generator, because if the fuel is methane, then you need to mix it with steam to reform it. And then you need a fuel mixer. The fuel mixer mixes it in the right proportion. You need a fuel preheater. Then same way on the air side, it's quite straightforward. But then again, on the exhaust side, maybe you want to split the electrode exhaust, do some recirculation, or maybe you want to condense the water out and store the hydrogen which is not used, or you want to burn the exhaust. So it gets a bit complicated if you go into a complex system. So here again, we have the SOFC stack in the middle. Then you have to condition the fuel to the inlet temperature of the stack. You have to condition your air at the inlet temperature of your stack. And then you have two separate exhaust lines which need to be managed in some way. So on a more broader system level, you have fuel which is supplied at room temperature. So if you look at this pink box as a system, you have fuel stored outside and it is normally at ambient or room temperature. So that has to be conditioned to 600 to 800 degrees, which the SOFC stack operates. Same goes with the air, which is at ambient temperature, needs to be preheated. And then you have to some way manage what to be done with the exhaust, which is coming out. So depending on the system design, you can either have one exhaust or you can have multiple exhausts. So this is completely up to the system designer on how the system is designed for which application. So coming to the most promising applications for solid oxide fuel cells. So when the research started more than 2-3 decades ago, and people were looking into all kinds of applications, distributed power generation, passenger vehicles, heavy duty vehicles, maritime, trains, etc. But as the technology progresses and we see other competing technologies coming into these applications, the most promising applications for SOFCs till 2030 is mainly in the marine sector and the distributed power generation sector. Because if you take passenger vehicles, my personal opinion is battery vehicles can easily do the job or can meet all the requirements for passenger vehicles. There is no need to use a solid oxide fuel cell in a passenger vehicle. Makes no sense. Primarily due to the high temperatures involved. But if you look at a marine application, if you look at an ocean-going vessel, it's not quite possible to electrify these ocean-going vessels. They need a liquid fuel source, and normally they are operating at a constant load level. So SOFCs are perfect fit for maybe a marine application. Or if you want to replace your power plants with more distributed power generation or microgrid kind of architecture, then SOFCs can also be a very good option. So these are the most promising applications that industries and other customers are currently focused on. And after 2030, maybe there is also some applications in the aerospace industry. So when I say aerospace, I don't specifically mean airplanes. I also mean airports, all these power units which are used at the airports, auxiliary power units used on the plane, maybe not completely to fly the plane, but other power generation units which are needed in the aerospace industry. So these are the promising applications. Let's take a look at some real world applications. So this is a SOFC system made from tubular SOFC stacks, like what I mentioned a little bit earlier on one of the slides, because you see it's mainly a big cylinder where huge tubes of SOFCs are placed inside with a complete system packaged in. This is made by Mitsubishi Heavy Industries in Japan. And the concept is you have a sewage plant, you have some sludge coming out, process the sludge, get out the biogas, and biogas is mainly methane, but with a low purity. So you purify that biogas, get methane out, put the methane into the SOFC, and then you have electricity and heat. And so it's a clean, real world application of power to waste. So who are these players and what are they doing, or who is really active in this SOFC business across the world? Here is a good map of which players from which regions of the world are quite active. Let me start from America. So in America, you have Bloom Energy and Fuel Cell Energy. These two companies are focused on high temperature fuel cells. Bloom Energy is a pioneer in SOFC technology. They make everything themselves, cells, stacks, systems, everything by themselves. And they don't sell the stacks and the systems, but they sell you the concept and for the electricity that they generate. So the business model is mainly focused on selling electricity dollar per kilowatt for a very long period of time. Then we come to Europe. We have system manufacturers like Bosch, Viessmann, Convion, and ZEG Power. And these system manufacturers, they buy stacks from the stack manufacturers like Elcogen, Sunfire, Solid Power, Ceres Power, mPower. Then we come to China and Japan. We have lots of stack manufacturers and lots of system manufacturers, especially in Japan, because there is lots of subsidies for hydrogen and fuel cell activities in Japan. So compared to the conventional battery technology, there are not too many players, but there are quite a few players also in the SOFC business because the applications are quite unique, which cannot be met by battery technology. So that completes the first part of our presentation, where I took you all through some basics of SOFCs, gave you an oversight of some cell design, stack designs. We saw how a basic SOFC system looks like, how a complex SOFC system looks like, what are the promising applications for SOFCs, and then who are the major players involved in the SOFC business. Now, AVL as a company, we are always at the forefront of new technologies. We want to get involved in novel technologies which will advance our business, and we don't want to stick to one technology which might get outdated and then we lag behind. So we are always innovating, always coming out with new ideas. So what are we doing in this SOFC technology business? So from a testing and instrumentation point of view, I will give you an insight. So the drivers for solid oxide technology is a rise in renewable energy power sources or its intermittent nature. There is increased installation of these renewable sources. And because of that, there is a need for seasonal energy storage. So gas is emerging as a big player for providing energy security. And you need fuel flexible and high efficient, high return technology, which can contribute to power outages and minimize the blackouts that we have during summer months and during thunderstorms and etc. So these are the drivers for the solid oxide cell technology. So what is AVL doing in this? So we have over 20 years of experience in solid oxide fuel cell system development. We have worked with so many research projects, both national funded Austrian projects, as well as European projects and international projects. So we have gained quite a lot of system experience in how to design range extenders or combined heat and power systems or a 200 kilowatt SOFC generator or even a 1 megawatt SOFC combined heat and power plant. We know what kind of engineering goes into it, what kind of components need to be chosen, how each subsystem works, etc. So we also have SOFC as a test field. We do both internal R&D and we can also offer testing as a service. And we would also like to take many of the synergies that we see from the PEM fuel cell world into the development tool chain for solid oxide fuel cell. So where does solid oxide cell technology stand as on 2023? Definitely an emerging technology. So this graph is normally for all novel technologies which make into the market. You start with an emerging technology, then it has got a growth phase. Then after the growth phase is over, the technology matures. And then after a certain time, it declines because there are new technologies coming in here, which will replace this. For example, the IC engine 100 years ago was somewhere here. And then it grew a lot during the 1970s, 80s, 90s. It got matured. And now there are other technologies which are taking over the IC engine technology. So solid oxide cell technology is currently somewhere here. Definitely an emerging technology. And within the solid oxide cell technology, we have 3 different categories. I mainly talked about SOFC, which is solid oxide fuel cell technology. But we also have SOEC, which is solid oxide electrolyzer cell. And we have RSOC, which is reversible solid oxide cell. So this only does fuel cell operation. The SOEC does electrolysis operation. And the reversible SOC does both in one stack or in one cell. So let's go down to the technology readiness level. The SOFC is quite ready. So greater than 8 means market ready. There are well-proven systems in the field. The technology is ready to market and there are active players in the business. SOEC, it's somewhere between 5 and 6. There are not too many players in the business as on date, but they're coming up. The technology is expected to mature in the next 5 years. And the reversible solid oxide technology is still at the lab level, at the research level, and maybe it takes about a decade to mature. So this is where we stand with the solid oxide cell technology as on date. So what are we doing from AVL ITS, Instrumentation and Test Systems? Based on the applications that I showed you before, where we have residential CHP, we have marine systems, portable systems, and distributed power generation systems. We have a dedicated test bed, which can cater to each and every application. For example, if you take a residential CHP, the maximum power size is limited to 5 kilowatts because this is what gets into every home. This is the size which gets into every home. So we have a test bed which can be used to test such a system. And it comes with a range of equipment around the test bed. If you move to marine applications or small business generators, the power size is somewhere between 50 to 160 kilowatts. And we also have a test bed which can provide you the environment for testing such a system. And finally, if you go up to higher powers, up to 400 kilowatts, we also have a system test bed which can be used for testing these big power generators based on SOFC technology. So just using the power class, we categorize them as ULD, which is ultra light duty, and heavy duty test bed. So what kind of tools are available from AVL? Right from simulating SOFC systems, SOFC stacks, we have a range of tools which can be used. We also have SOFC single cell test bed. So if you are a cell manufacturer or if you are a research institute who manufactures cells or make cells and want to test the performance of these cells, we can provide you with single cell test beds. We also have stack test beds. Up to 50 kilowatt stacks can be tested here. We also have virtual SOFC test beds. So if you're not so keen on investing in hardware right away, but just want to test a few things in a virtual environment, that is also possible. And then we have our SOFC system test bed where you can test real systems together. Besides that, for the stack manufacturers, we also provide SOFC sintering stations. This is a key step in SOFC cell and stack manufacturing. So we have a complete tool chain for the SOFC system development, right from simulation level all the way to big systems. And this, we do it with our partner Greenlight Innovation. So this is a company based in Vancouver, Canada. And AVL wholly owns this company, but we still keep the name Greenlight Innovation because it's well known in the cell and stack test bed environment. So what kind of tests do we have to do on a system level to make the system approved? So this is not only valid for SOFC, but this is also valid for any system that makes it into the market. So any IC engine system, any battery system, anything else that makes it into the market has to go through a range of tests to prove that the system is actually working, and you have to get it certified before putting it into the market. So with the SOFC system test bed, what can you do? You can do system ramp up and ramp down tests. You can do a system performance test. You can do a thermal load test. You can do an emission test, acoustic test, and the final acceptance test. The green boxes below are a bit more detailed on what you can do exactly in these. For example, if I take up the system ramp up, ramp down test, you might want to test how fast can the system start from the cold state, or how fast is the system able to respond from a warm standby state. What happens if it's shut down immediately? Does it affect the system? Does it affect any balance of plant components? So these kind of tests can be done in this category. Let me then jump to the emission test. So if you use fuels other than hydrogen, for example, ammonia, methanol, or methane, then you might have some species in your exhaust, and maybe you are interested in analyzing how much of this got actually used in the solid oxide cell and what kind of species is coming out from the exhaust. Because eventually you need an emission certification to say that my system is low emission and high efficiency. So you need to do this kind of a test on the system level to get it certified. And the other tests are similar, digging deep into what kind of tests do we need to do. So now we talked about testing. We talked about the need for testing and what kind of tests you can do, but how does a system test bed actually look like? Here you see a block diagram or a schematic of how the system test bed looks like. So in the middle, you have your unit under test or UUT. So this is your complete SOFC system. Could be a 5 kilowatt system, could be a 100 kilowatt system, could be a 400 kilowatt system, doesn't matter. So what we provide is the environment around the unit under test or the system so that the customers or the research institutes, whoever is testing it, can test the system in a reliable and effective way. So you need a fuel supply unit. So we have our AVL Hydron or Gastron, which is supplying methane or hydrogen with flow measurement. And then you have the air intake system coming from the test cell. You have a certified test safety system, because you need to make sure that your unit under test is protected at all times, your test facility is protected at all times, your lab technicians or people working on the test bed, they are protected all times. So there is a certified safety system. Then you have a e-storage, which emulates the battery, and it also emulates the grid. Then you have a low voltage DC supply for all your sensors and electronics. Then you have a coolant conditioning system. If you use power electronics, which generate high amount of heat, then you need some kind of a coolant system to remove the heat. So we have the coolant conditioning both for power electronics and for process heat recovery from the SOFC. Then in case something happens in an emergency, you need a protection gas supply, which is a hydrogen-nitrogen mixture. And then finally, you have an exhaust module, which will safely suck out all your exhaust, condition it, and vent it to the atmosphere. And then this whole test bed has to be working in a way where you don't want the operator sitting in the room all day. You need some kind of an automation system where you just say, run the test from X period to X period for this load, and you can program it. That's where the AVL Puma fuel cell test system automation system comes into play. So it controls all these equipments along with the test bed and gives the operator the flexibility to make the system testing very easy and hassle-free. I just put down this comparison compared to the engine testbed, which many of us are already aware or have seen in their universities. Maybe you had a field trip to go to some company to see, but maybe many of you have not seen an SOFC testbed. So some comparisons are both operate at high temperatures. Engine testbeds somewhere around 400 to 500 degrees, SOFC more than that. There is fuel injection on both kind of test beds. There is air injection on both test beds. You need to treat the exhaust on both test beds. You need to control the fuel supply and the air supply on both test beds. The only difference is the engine needs a coolant. If you look into your car or your truck, you see there are dedicated oil channels built into the engine or some coolant channels which keep the engine cool, but there is no coolant in the SOFC stack or system. The thermal management is completely via the airflow in the SOFC. So these are the major differences between the engine testbed and the SOFC testbed. We also provide a complete lab in a container. For example, that you see here, it's not like a standard container which is on the ship, but we custom make these containers. And if an institute or a customer doesn't have the lab space, Then we put all this equipment that I showed before neatly packaged into a container, and then you have a container lab which can be transported anywhere that you want. And if you change your location, you can easily pick up this container, put it in a new location, and you still have your SOFC testing lab up and ready. In this world where we are moving more towards software and Internet of Things and all this, the differentiating factor is not the hardware, but you need high-class software products too to make testing and test beds more intelligent, more easy, user-friendly. So we have a range of software suite in AVL for different applications, but specifically for SOFC, these are the 4 main softwares that are used in SOFCs. So the AVL Cruise M, we have the Cameo, we have the AVL Puma automation, and some Concerto, which is a data analysis software. So Cruise M is mainly used for simulating systems. Cameo is mainly used for designing your experiments to make it more automated. So if you want to make a performance test, you write some kind of a software code in Cameo to say, run the system from this point to that point. So it's more like a design of experiment software. Puma is your automation system for your test bed, and Concerto is mainly data analysis. So once you have a test completed, you have loads of data. And if you don't analyze the data, you cannot make any meaning out of the test. And if you cannot make any meaning out of your test, there is no point in doing the test. So this helps in data analysis when you have large amounts of data. I would like to give you an example of how to do a system performance test. So for example, how is it done? So we have the whole set of hardware and the software modules that were shown before, which comes into place, and it interacts seamlessly with each other. For example, once you have your solid oxide fuel cell unit under test, you have all these things coming into place and working together onto your test bed, where your unit under test is interacting with the different units, and each unit is interacting with the other units, and in turn controlled by your test bed automation. So with this kind of a system performance test, what data can you collect? You can collect information about the stack polarization curve. You can have information about the electrical efficiency of the system. You can make design maps for various variables. For example, if you have temperature versus current density, how will your system efficiency look like? Or if you have pressure versus current density, how will your system efficiency look like? Then you can have some information about exergy flows, not energy flows, but exergy flows, which is based on second law of thermodynamics. And from all these tests, how does it aid in product development? Because in the end, you need a working product in the market, which normal people or normal customers like you and me can use. So it provides information on how the system behaves at different operating points. What operating points should it not be operated in? What is unsafe operation? All this information can be got. Then you can run the system with different fuels. You can measure the fuel consumption rate. And if you know the fuel consumption rate, you can also have an estimate on the efficiency of the system. You can check how the system responds to different load conditions. You can also understand the system control strategy. So all these aids in product development in bringing out a successful product to the market. So that concludes second part of our presentation. So we saw what AVL is doing from an instrumentation and test systems point of view for the solid oxide fuel cell technology. So we have cell test beds, we have a range of software suite, which can help people. We have hardware for different parts of the test bed. And we also do testing as a service. So all these things are there for the solid oxide fuel cell industry and for the different players involved in the SOFC business. Now I would like to take the audience through the project called Fuel Sum. So what is the project about? So we wrote this proposal back in 2021, where the call was from the European Union about climate-friendly, high-risk, high-return technology, which can reduce emissions by about 50%. So emerging technologies for a climate neutral Europe, this was the call. And we wrote a proposal in a way where we want to focus on ocean-going vessels, because the end application we saw was this is a very hard to abate emission sector, because the powertrain on the ship is currently based on diesel engines, very, very large diesel engines, like almost the size of a building, of a two-story building sometimes. And emissions are quite high, noise is quite high. So we said, okay, let's try to use solid oxide fuel cell technology, which with these three different fuels, ammonia, methanol, and hydrogen onto the ship, and see if we can actually build such a big system. But since the project will only showcase a system on a lab scale, so we will showcase a 6 kilowatt system, but we will of course carry out some studies to show how the system can be scaled up to the megawatt range. So this is what the project is about. It started last year in September 2022 with AVL as the main coordinator, and we have about 7 other partners from different European countries looking into different aspects of the project. So here I need to acknowledge the EU for granting this. So it is granted under the grant agreement 101069828. And the vision of the project is to find a scalable and flexible path for a multi-fuel system, ammonia, methanol, besides hydrogen, to act as key contenders to replace marine diesel as the fuel on ocean-going vessels. So using solid oxide fuel cell technology. So this picture greatly summarizes what the project is doing. So on the left side, we have the fuel pathway. So right from production up to the port, how can you make the fuel pathway more green, more environmental friendly with these three fuels, ammonia, methanol, and hydrogen. In the middle is the application itself, which is the ocean-going vessel. And then in the ocean-going vessel, you have the SOFC multi-fuel system. So the goal is, if the fuel changes in the future to either ammonia or methanol or hydrogen, it should not matter as long as you have engineered the system in a way which can work on any of these fuels. So then your technology on the ship is ready. And if the legislators or the International Maritime Organization changes the fuel, that should not matter, because the power generator on the ship is a multi-fuel energy generator. A little more elaboration from the project. So from work package 1, so the project is divided into several work packages. And from work package 1, we look into the value chain of how the fuel pathway can be more sustainable, as I said before, and also model a scenario as to how this fuel can be brought to different ports, which will then use the fuel on the ship. From work package 2 and 3, we want to have the SOFC stack validated with ammonia and methanol as the fuel. We want to have a multi-fuel reformer before the stack, which will precondition the fuel to the standards needed for use in the SOFC stack. And we also want to do some fundamental science on understanding what will degrade the stack if you use these fuels. And we will also build a system, a lab scale demonstration, and test this system under artificial marine conditions. Work package 4 mainly looks into the life cycle analysis and the techno-economic analysis, because these days it's not only important to showcase technology, to showcase science. You should also do an analysis to see if this technology has an environmental impact. Will it actually lead to reduced emissions, or will it lead to more emissions? Because if it leads to more emissions, then we should not do it. So that's what work package 4 looks into. And we have also some targets within the project. So we want to reach a system efficiency of more than 50%. We want to ensure that on a lab scale, the system runs for at least 500 hours. On a stack level, we want to achieve more than 55% with ammonia and methanol. The impurity tolerance should be improved by 30% from the current state-of-the-art technology. We will demonstrate a technology readiness level 4 prototype. We will test it under marine operating conditions. And from the LCA, LCSA, and the techno-economic studies, we will show that there is a potential for 50% reduction in greenhouse gases with this multi-fuel system based on SOFC. So some of the research hypotheses that we are investigating is, can we have a single component which can reform different fuels? Can the SOFC operate on methanol and ammonia? And does it need a suitable design window? What degradation happens if you use these fuels? Can it operate continuously, or will it break down after a few tens of hours? Can we define fuel quality requirements which are being produced from different sources? And is it possible to build a fuel supply pathway all the way to the port, which is environmentally friendly? So these are some of the research hypotheses that we are investigating in FuelSum. There is also a dedicated website for people who are interested in knowing more about the project. So we completed 1 year, and that's the website if you are interested in looking into what this SOFC is about and what every partner is doing about this. And finally, that's my contact information for people who are interested in this technology and want to get in touch with me, or want to get in touch with anything related to solid oxide fuel cell or hydraulics. That's my contact information. And I'm sure this presentation will be shared with the audience as well. And yeah, that brings me to the end of my presentation, to give some room for questions and discussion. Thank you very much.
Thank you very much, Dr. Vikrant.
Yeah.
I think the presentation was quite impressive, and it made everybody got interested in the session.
Thank you.
Yeah, it is very, very interesting. You have done a lot of work. I have seen your profile as well. It is very much motivating. So audience, please feel free to ask the questions. If anybody has any question to ask, please raise your hand. I can unmute them, or you can put them in the chat box. Anything is
anything is fine. Yeah.
Yeah. Of course, if the speaker is comfortable.
Anything is fine. You are the moderator. I'm okay with answering any questions.
Thank you. Thank you so much.
Yeah.
I think we
Sir,
are getting
will take maximum question 1 or 2. So anyone kindly post in the chat box.
Somebody has raised their hand. Tatvam Joshi has raised his hand.
Ask unmute. Yes, sir. Please, Joshi. Joshi, sir.
Yes, sir. So session was very nice and informative. Sir, my doubt is related to the software that was used by AVL. So what is the performance they are testing in the PUMA? AVL PUMA.
PUMA. Okay.
Yes.
So PUMA is a German acronym for the software for the testbed automation software. So what it does is, once you have your test bed ready, it automates your test procedure, and it automatically controls different parts of your test bed, so that you as a operator or you as a researcher need not sit in the lab the whole day waiting to do a test. So it just makes your life a bit easier with automating the whole test procedure. So it's just an automation software with a GUI interface, a graphical user interface.
Hello, sir.
Oh, we have Naresh.
Yes,
Naresh.
please.
Sir, very good morning, sir. I don't know. It is morning.
Good morning.
Yeah. Actually, I'm myself, Naresh. I did my PhD. I'm about to complete my PhD in the area of thermal energy storage by using phase change materials from BITS Pilani.
Yeah.
Yeah. So I have a couple of queries. Will the high temperature operation of the SOFC affect the performance of the SOFC?
So your question is, will the high temperature affect the performance?
Yeah, operation performance.
Okay, so every cell manufacturer and every stack manufacturer has their own novelty in terms of materials, and they know what is the temperature limit.
Yeah.
So if you exceed what temperature limit that they provide you, for example, if say manufacturer X tells you you should not operate more than 700 degrees with my cell or my stack, but if you exceed this, then there will be a performance degradation. But as long as you stick to the operating window, I think it should be okay.
Okay, so another connected query is, you mentioned in your presentation that SOFC is very good enough to work with only thermal management with air flow. Right?
Yeah.
Whether only air supply is enough to manage the temperature to make it more efficient fuel cell?
So the way the thermal management is done is, if you increase the current density of the cell, then there will be more heat generation. So when there is more heat generation, there is automatic control block in the system, which says you have to blow more air through the system to bring down the temperature to the level of the stack.
Yeah,
so
that's what is my detailed query is air supply is enough to manage the temperature? Even though if I'm increasing the flow of air, whether other mode of thermal management is required as far as this SOFC is concerned.
As on date, you just have the air. So you need to size your air blower in a way which can blow enough air to cool the system. But as on date, there is no other thermal management technique. But if somebody else comes out with a new technique, that will be very helpful for the technology as well.
Yes, sir. That is what my query. Actually, you mentioned your company is involved in R&D and going with so many ideas to improve that. So, have you faced any problems with air blower capacities? If it is keep on increasing, whether it is going to have any problem for the system?
The biggest problem with, if you operate the air blower at the highest capacity, it reduces your system efficiency. That is the biggest issue that we face.
Yeah, that is what. So why can't you think about another thermal management systems to address the issue?
But then we also have to think about fluids which can work at 600 degrees.
Yeah. That is what. So it's another way, right? It is one of the possibilities of exploring the new ways.
Of course. There is always possibilities.
As a thermal management engineer, I'm very much interested in that area.
Yeah, of course.
It's a wonderful talk, sir. I got so much information from the scratch. You taught very well. We understood each and every word without any information known to us earlier before this talk.
Okay.
That is what I'm very good thing about your presentation.
I was not exactly sure what the audience, who the audience is, so I thought maybe I will structure it in a way where it gives some basics, present some AVL activities, and then present some EU project activities.
Very well organized, sir. We learned a lot about SOFC, about your company, and that project as well. So
thank you. Yeah.
I would like to be in touch with you with your permission.
Sure. Absolutely. I will share this presentation with Dr. Vishwanath, and he can send it to everybody.
Yeah.
Yes. Please, sir. Thank you, sir. Thank you very much.
Yeah.
Thank you, sir. Thank you. Let's give a chance to Dr. Muthukumar. Ask a question. Yeah. You can unmute now. Yeah.
Yeah, Muthukumar, sir, please.
Yes, sir. Sir, I have one question, sir. So, where we are commercially using this SOFC, sir, for generation of power? Commercial usage of SOFC.
Where are we using it? So, hello, can you hear me?
Is it commercially used for power generation at anywhere?
Yes.
Is it audible, sir?
Yeah, audible.
Yes, sir. My question is, where we are using it commercially for power generation? Is it used at anywhere?
Dr. Vikrant has understood your question. He is answering.
Yeah.
Yes, sir.
So, it is definitely commercially used, and there are several locations in Europe, also in Japan. I don't see a location in India, but I think also in Bangalore, Bloom Energy has come out with a concept to use biogas from farm waste for data generation, for data center power generation in somewhere near Bangalore. This is in concept study, I think. Yeah.
Yes, sir. Yes, sir. Okay, sir. So you are generating for various ranges of SOFCs. I actually in a slide you showed that up to 1 megawatts power generation capacity you are generating. Is it right, sir?
We have done projects up to 1 megawatt. Yeah. Let me go back to the slide.
You are,
please go ahead.
Yes, sir. Yes, sir. It's my question. What will be the cost of that 1 megawatt system, sir? SOFC.
As on date, 1 kilowatt of SOFC is about roughly $3,000 to $4,000.
Okay, sir.
Yeah, but this is just the SOFC. But
in
then
1 megawatt, sir.
So I don't know the cost at 1 megawatt level, because there will be all these blowers and pumps and heat exchangers, everything put together. But on a stack level, 1 kilowatt is about somewhere between $3,000 to $4,000.
Okay, sir. So what are the durability and reliability of this SOFC, sir? Compared to conventional, is it that much of reliable and durable?
Yeah. So if you, since the SOFC doesn't have a good dynamic response, the best application is where you need constant power generation. And if you use it in an application where you don't cycle up and down too many times, then it's got a reliability of more than 5 years, after which you can replace the stack.
Okay, sir. But what about the cost of the power generation cost, sir, compared to conventional? What about this conventional? Compared to that, what is the cost of power generation per unit or some kilowatt per hour?
The cost also depends on
much higher.
Of course. As on date, it is much higher because it is not scaled up in a way compared to conventional technology. And it also depends, if you manufacture more, then the cost comes down, and that will also lead to reduction in cost. But you are right, as on date, it is more expensive than conventional. But if more regulations come in, if more government rules come in that you cannot have emissions, you cannot have other things, then you need to switch to clean power generation technologies.
Yes, sir. Thank you, sir. Very good presentation, sir. Thank you.
Thank you.
Participants, I think the next speaker is ready for his speech. So we all let us congratulate Dr. Vikrant for his session. It's been very elaborative and very informative and more technical as well as the basics. He covered everything. Thank you so much, Dr. Vikrant.
Thank you. It's my pleasure. Yeah.
Thank you so much.
You, sir.
Let's be in touch. Thank you very much.
Yeah, we'll be in touch. Yeah. Thank
you.
you. Have a nice day. Bye-bye.
Thank you, sir. Thank you. Bye.
Bye, sir.
Anuhya, madam.
Yes, sir.
Please welcome our next speaker, who's a professor from IIT Madras, is an eminent speaker in chemistry. We welcome you, sir, for this session. Thank you. Thank you. Ma'am, please continue.
Thank you for the question, sir. So, Dr. Vikrant Venkataraman, sir. Now, it's an honor to have Professor Kodandaraman Ramanujan, sir, Department of Chemistry, IIT Madras, to have joined us today. After 2 successful postdoctoral studies at Michigan State University, East Lansing, 27 to 29, 2009, and National Research Council of Canada, Ottawa, 2009 to 11, he joined the Department of Chemistry, IITM. Dr. Kodandaraman's expertise as a fine electrochemist of the country is focusing and contributing to realize India-centric solutions for the ever-growing need of energy storage and conversion. Therefore, his motivation is in the direction of developing new functional materials, redox active, organic molecules, and utilization of abundant resources such as sodium and zinc towards developing of newer energy systems. The academic research pursuits under the broad headings of lithium, sodium, zinc, vanadium-based batteries, organic dyes for solar cells, and sensors have enabled delivery of translatable research besides the photophysical and electronic properties of the redox active organic functional materials developed by molecular engineering for sodium, lithium, zinc ion batteries. The audience is eager to benefit from your knowledge, sir.
Thank you, madam. I hope I am audible.
Yes, sir.
Yes, sir, you are audible, sir. Perfectly fine.
Okay, so what I'm going to do, see, I believe the audience are, some of them are faculty and you have some students as well, right? Or something different?
Yes,
That is true, sir. We have faculty, mixture of faculty and students, both.
Okay. So as I committed, I am going to use EndNote and a few slides to conduct my session. So this is going to be on a qualitative discussion on the impedance spectroscopy for the fuel cells. So not much on the research side, but more on fundamental side of characterizing the fuel cells using a non-destructive technique called impedance spectroscopy. Okay, so just to confirm whether you are able to see my screen, I'm going to share screen. Share screen. You are able to see my screen, OneNote screen?
Yeah, it's coming.
Yes, sir. Yes, we are able to see.
Okay, thank you. So now I need to find out how to minimize. Okay. So I take as a, I'll put my video off. Probably you may not be seeing the right orientation because I have my iPad in my table. Yeah, now it should be fine. Yes, you are seeing my OneNote, right?
Yes, sir. Yes, sir.
Okay, yeah. So for today's discussion, we'll take a case study of a polymer electrolyte membrane fuel cell. It's called PEMFC. Some of you may be knowing, those who are familiar with this, that is in this fuel cell, we have a anode. Okay, we have anode. And then we have a polymer electrolyte membrane, which is generally proton conducting in nature. So it will conduct a proton through it. And then there is a cathode where the reduction happens. So the typical reaction in the anode is hydrogen getting oxidized to proton plus 2 electron. So these protons which are produced here is the one which goes through the membrane and then reaches the cathode, where suppose if I have 2H2, then it is going to be like 4H plus. It's not selecting. It's 2H2, then it's going to be 4H plus 4 electron. Then this 4H plus will go to the other side plus 4 electron. plus oxygen gives you water. So the entire reaction, if you sum it up, because each one is a half reaction, so you sum it up, it's going to be 2H2 plus oxygen giving water. Okay. So this reaction, according to thermodynamics at standard condition, has a delta G value of less than 0. So if it is so, then it should be a spontaneous process according to the definition of from the thermochemistry. But you take a hydrogen from a cylinder and let it go into our atmosphere, which has oxygen, we don't see water forming immediately. That means there is something preventing this reaction happening. So we call it as a kinetic limitation. What is kinetic limitation? Because delta G is less than 0, thermodynamics predicts this reaction should happen. But thermodynamics does not say anything about what is the speed of the reaction, how fast the reaction has to go. So currently this reaction is going at very dead slow speed. Okay, so how do we accelerate then? We have to have a catalyst to accelerate the reaction. In other words, if you know the kinetics, you can look at like this. This is my reactant profile. That means H2 plus O2. This axis is energy axis, and this is a reaction coordinate axis. Then you will see this pass through this is a product. Okay, product is water. So if you look at it, basically, this will be a potential energy profile of your reactant, and this is your potential energy profile of your product. Okay, they merge like this, so only this portion, merging portion alone, we have taken and you have plotted. Okay, so this is your reactant state, this is your product state. Product is at lesser energy than your reactant. Therefore, the delta G is negative as per the thermodynamics, but this reaction has got a huge activation energy. So the activation energy is so much that the thermal energy surrounding these molecules in our atmosphere is not able to take these reactants to this transition state. So they go somewhere here and come back, somewhere here and come back. It never surpasses this activation energy barrier. Therefore, this reaction doesn't happen at appreciable rate. It's a really slow reaction. So then the way to speed up such reaction is to have a catalyst. The catalyst will kind of reduce the activation energy. Therefore, more of reactant can pass this barrier and go to product side. So then what is the catalyst used? Catalyst used generally a platinum nanoparticle supported on carbon. This is a catalyst used for both anode side and cathode side. Okay. So now we know the reaction, which is 2H2 plus O2 giving you 2H2O, which is a 4-electron process. Therefore, the delta G that you get out of this process is NFE. F is Faraday constant, which is 96,500 coulomb per mole. And E, the voltage of this process at standard condition is 1.3 volt. So you multiply that, you get it in certain number of joules. So that is the energy that you get out of this reaction when you react 2 moles of hydrogen with 1 mole of oxygen producing 2 moles of water. Suppose if I change the number of moles, because this is the delta G of the reaction. Delta G of the reaction means it depends on the amount of reactant that is present. Suppose I have like this 4H2 plus 2O2 giving you 4H2O. Then you have taken double the amount of hydrogen and oxygen. Therefore, the energy you get out of this reaction, delta GR, would be twice the amount of what you got here. If I call this delta GR1, then delta GR2, that is for this process, is twice the amount of delta GR1. Okay. So this is how we understand, the thermodynamics and the kinetic limitation which prevents this reaction happening, and how we are overcoming. We are overcoming using a catalyst in the anode and cathode side. So when you make the fuel cell, it's very important. We need to understand the quality of that interface and how it behaves over the time, because the fuel cell slowly lose performance with the time. So then we need to have a technique by which to assess the health of this fuel cell with the time without opening the fuel cell. So in that scenario, the impedance is an important tool which can tell you the state of health of your fuel cell without having opening the fuel cell. Okay, so that's a kind of thing that I would like to give as a preamble. And after this, I am going to show you an animation. Before that, so this fuel cell has an anode and a cathode, and you have an electrolyte in between. Then fuel cell is a galvanic device. That means it produces energy for you. So if you put it in the circuit and variable resistor, by changing the resistance, the current that flows in the circuit can be changed. So this is the direction of electron that is flowing. Okay, this is the direction of electron that is flowing, because hydrogen is oxidizes to proton. While oxidizing to proton, it liberates the electron that goes this way. So by changing the, by varying the resistance in the circuit, we can vary the current that is flowing in the circuit. Generally, you might have seen this, the voltage versus current plot. This is called polarization curve of fuel cell. So ideally, it should be 1.23 volt. But the moment you start drawing current, then you will see a potential drop. That's called activation polarization in case of fuel cell. After that, this will follow a slopey line. That's because of IR drop. Because as you draw more and more current, the electrolyte poses a resistance to the flow of ions within this medium, right? Therefore, you have a IR drop. Also, you have a contact resistance in the cells in multiple places. So all that will show as IR drop. And then you will hit a mass transfer limiting region. Mass transfer limiting region means your catalyst is ready to do the reaction, but you are not able to supply the reactant at the speed the catalyst want. Therefore, you'll have a mass transfer polarization once you go beyond certain current density. So this is a current density region in which you can operate your fuel cell. Generally, people do also the power curve. How will you produce power curve? You take the voltage and current at each point in this line, and you multiply them together, you get the power. So the power curve will be somewhat like this. Okay, so if you call this as a power axis, then there is a maximum power at particular current. Okay, so this is so generally people operate fuel cell in this region around the maximum power or before that, not after that, because that is a very unstable region to operate the fuel cell. Okay, so now let's go to the animation. How to come out of the slide. So now you can see, are you seeing my slide?
Yes, sir. Yes, sir. It is visible.
We are able to see your slide. Yes.
Okay. Yeah. So if you see my animation, you can understand I have put here a cluster with a lot of atoms of different element. Okay. So there is no such cluster, but the idea behind showing this is the way I look at electrochemistry is something which is like equivalent to n number of catalysts that you know in the literature. Because if you look at it, the activation line, the reactant becomes a product, right? This is a potential energy, this is a reaction coordinate. Reaction becomes product, but if you change the catalyst will give you another route wherein the activation energy may be smaller. Therefore, the reaction goes at much faster rate than before. Okay. So that means this is catalyst 1 and this profile is for catalyst 2. You may have another catalyst which may do like this. This is for catalyst 3. Okay. But imagine instead of changing every time a catalyst and making the reaction go fast, imagine I change only the potential and make the reaction go fast. Okay. So that is what your electrochemistry. In electrochemistry, what each and every catalyst that can do, we can do it with one single electrode, just changing the potential. So each time I apply a different potential is equivalent to having some catalyst. Okay. So that's why I visualize it this way, like it is a collection of catalysts. The electrolyte interface with the suitable potential. I can change the potential, I can make the rate of the reaction go differently, So therefore, I visualize this as a kind of a thing wherein it is equivalent to a collection of catalysts. Okay. So now, moving to the next slide. Now let us look at this animation. See what I have done here. I have drawn 3 activation profiles. The first one here corresponds to the equilibrium condition. Equilibrium condition means both the product and reactants are at almost same energy. There is the rate at which the forward reaction happens and rate at which the reaction happens are at equal rate. Okay. What I have done here, I have applied over potential. Okay. By applying over potential, I can shift the energy state of my reactant from here to here. What it did, it has reduced the activation energy. So this was the activation state. So this was the starting point. So this gap from here to here is the activation energy. By taking this to here, I have reduced the activation energy. But the point is, when I take the potential from here to here in order to reduce the activation energy, also the activation state moves a little up. But the point is the activation state did not move up as much as my over potential moved up. So the over potential is NF eta, where eta is the over potential, which is defined as the applied potential minus the equilibrium potential. This potential is a standard potential if we are doing a fuel cell at standard condition. So this difference, the applied potential to equilibrium potential difference is called over potential. So this is over potential. You multiply by N and F because this is a charge, this is a stoichiometry. So you multiply them, this gives in the unit of energy, right? So this axis is energy. Therefore, I multiplied over potential with the N and F. By this way, I can show in the same graph of energy versus reaction coordinate how if I shift my over potential, the energy of the reactant goes up. But it went up by NF eta, whereas from the activation state from here to here, okay, that shift is only alpha times NF eta, where alpha is less than 1. What it means, only a fraction of the applied energy has gone in increasing the activation state from this value to this value. But this value alpha NF eta is less than, okay, alpha NF eta is less than NF eta, okay. So I have raised this much energy, but only little bit here raised. So therefore, there is a net decrease in the activation energy, okay. There is a net decrease in the activation energy. Therefore, I am going to read in the animation. You can see the first ball moves very slowly. The second one moves a little faster. Third one moves much faster. Why? Because the net increase or net decrease in activation energy is higher for this case. The net decrease in activation energy is higher for this case, and compared to this, slightly less for this, and very, very less for this. Therefore, by changing by manipulating the over potential, I can take the reaction go faster or slower. Okay. Therefore, I said this potential, the collection of potential is equivalent to the collection of catalysts that in conventional chemistry that we do. So we can also approach it in a mathematical form. Let us assume there is an activation energy. So the activation energy for the forward reaction, F stands for forward reaction. So now I decrease the activation energy from going from here to here. How? By decreasing by so much, minus NF eta. But at the same time, what happens? The activation energy also goes up little bit. How much it is going up? Alpha times NF eta. Okay. So therefore, net change in activation energy is the initial activation energy at equilibrium condition. Then how much you shifted by applying potential, and how much the system shifted itself with the activation state. All that you have to add. Then you get what is the net activation energy. Okay. With over potential, this net activation energy will only decrease. Now let's go back to the chemical kinetics. In chemical kinetics, if you have a reaction A goes to B, and if it is a first order reaction, how will you write rate? Rate as K times, K is the rate constant of this process, times A, right? How will you write K? K in Arrhenius terms, you write K as omega, some frequency factor, e power minus EA, which is activation energy, by RT. This is how you write it in a regular chemical kinetics. I am going to start from there only. So here I have a rate constant times the concentration of the species, but I multiplied by N and F. Why did I multiply by N and F? Because the rate of the reaction will have the units of moles per centimeter cube per second, right? Because the concentration has a unit of moles per centimeter cube. The first order rate constant has a unit of second inverse. So the rate has a unit of moles per centimeter cube per second. I have to convert that into current or current density. How will I do that? I need to multiply by Faraday constant, which is so many coulombs per mole, and the stoichiometry involved in the reaction, which is N. When I do that, you can see this comes in the unit of coulomb per centimeter cube per second. And then the rate constant used here is not second inverse because it's a heterogeneous rate constant. So it is used in the centimeter per second. That is the rate constant unit here. So if you look at it, this will come into coulomb per centimeter square per second. Coulomb per second is ampere. So ampere per second, centimeter square. So let me erase this so that I can rewrite it. So now if you look at it, your current density is in the unit of ampere per centimeter square. That is nothing but I. Okay. So now what I have done, I have taken this conventional, activation, Arrhenius type activation, and then I am going to modify this with the activation energy which I calculated once I apply over potential. So I apply that here, and then I rearrange everything. Then you get this expression. What is this expression? I is nothing but I naught, which is exchange current density, e power 1 minus alpha NF eta by RT. What it means? That means the current will change. This is here. This is the current. This is minus alpha. So the current is changing with over potential. How it is changing? There is an exponential relation. Okay. So every time I change the over potential, there will be a current correspond to that. So that's what we looked at in the previous graph, where we had a voltage versus current, where you could see the fuel cell started with 1.23 volt. As I change the current, the voltage also changing. In other words, as I change the voltage, current was changing. That we call it as a polarization curve. That is governed by this equation. This is called Toffel equation. When you incorporate both the forward and the backward component of the reaction in a given interface, we call it as a Butler-Ulmer equation. So basically, what you need to appreciate here is the current and potential are related by an exponential relation. Okay, in absence of mass transport, the current and over potential are related by an exponential relation. So how do you understand that? Every time you increase the over potential, you will see current will increase. What is the analogy for that? You can take the standard activation curve. You can see as I decrease the over potential, there is a net decrease in the activation energy. Therefore, the reactant moves faster and faster to the product side as you increase the over potential. This is how we should understand this example. So what we have learned in thermochemistry, in kinetics, we can link to the electrochemistry this way. Okay. So now let me go back. Go to the third animation. Now what you see, so this is actually a cell. Okay, some cell. So in our case, what we did, we oxidized hydrogen and then product water has formed. Now let us assume that our product is water and then we are oxidizing hydrogen, or we can take any electrochemical reaction where anode, when it oxidizes, some product will form at the anode. Similarly, something will form at the cathode. Now let us take a generic cell like this. And what I'm going to do, I'm going to close the circuit. You can see the circuit here. I'm going to close the circuit. The moment I close the circuit, electrons start flowing in the between the terminals. When the electrons start flowing, you will see the products getting formed at the electrode. You will see the electrode electrolyte interface here. In this region, you will see slowly product forming. Meanwhile, you also see the profiles. This is a reactant concentration profile here, and this is a product concentration profile. You could see as you apply potential, the reactant which was very close to the electrode get consumed. Then the concentration near the electrode goes to less than the bulk value. Then what will happen? There will be a diffusion of reactant towards the electrode. So, and then the product gets formed on the electrode will diffuse out like this, right? So there will be a buildup of product near the electrode, and there will be a consumption of reactant near the electrode. So I'm going to rerun this video again. You can see as this video runs, you can see the concentration profile. The reactant concentration profile with the time is keep changing because the surface concentration keep on dropping, going towards zero. and the reactant concentration is keep on increasing because it is produced at the electron, it is very close to the electrode. So that's what you see in the yellow color here, which is the product that is formed. So the product, it diffuses out into the bulk of the solution. That's why you see the color changes as, kind of gradient in the color that I have given here in yellow color. Okay, so this is how you look at it when the reaction happens. How the reactant and the product profile will be around that electron. Okay, now you have seen this. Now again go back to the end note and look at now let's go to the end note. Hope you are able to see my end note again.
Yes, sir.
Yes, sir. Yes, sir.
Yes.
Okay. Yeah. So, so what I am going to do, generally, when you have an anode, when you have an electrode, anode, say cathode, and you have an electrolyte in between, this interface is actually modeled as a capacitor as well as a resistor. Why it is done? Because now we have seen current is proportional to, or current is equal to I naught exchange current density times alpha NF eta by RT. So current is related to over potential by an exponential relationship. That means when I change the over potential, I will be getting different current, which is equal to having different catalyst. So why, if you look at it, these are the factors which are here that the I naught value will decide how much current will flow for a given over potential. If the I naught value is very big, then for a small over potential variation, you have a huge variation in current. So I naught decides, this pre-exponential factor decides what will be the quantum of increase in current as I increase the over potential, right? So keep that in mind. So this situation can be related like this. So it is like you have a kind of a roadblock on your way. Okay, you are running now. So if the roadblock is very steep, then you will not be able to maintain the same speed that you are coming. You will be slowing down, and then you will slowly go that side. If the roadblock is very tiny, then it's easy, you can easily surpass. So this I naught kind of tells you that how big will be your velocity when you are changing the activation energy. This is a kind of that. So now what happens for the flow of electron? There is a resistant in the path. Okay. So that resistant for the flow of electron, we are overcoming using the over potential eta. Okay. So now we can look at this and also the ions that is produced which has to move in the electrolyte. So there is a resistance for the ions which are moving in the electrolyte as well. So let me put that resistance here. So this resistance is the solution resistance, which is offered to the movement of the ions. And let us look at this interface. In the interface, there are two things. Because this is an electrode-electrolyte interface, this can be viewed as an electrode in touch with the dielectric. So it's like a capacitor also. So you have a capacitance associated with this interface. Besides, when the reaction happens, the electron is transferred between the electrode and the electrolyte, right? So for the electrons to move, there is an activation energy that we have discussed right now. So there is an impedance for the electron to move back and forth between the electrode and the electrolyte. Therefore, that we can model it like a resistance. So this is called Faradaic resistance because whenever you have a charge transfer between the electrode and the electrolyte, we call it as a Faradaic reaction. Okay. Whenever there is no electron transfer, like a capacitor, EDLC capacitor, electrical double layer capacitor, charge moves from one electrode to another electrode, but it never crosses the electrode-electrolyte interface because it's always kept from one plate to another plate, but it never allowed to cross the plate, electrode-electrolyte interface. So that kind of current is called non-Faradaic current, or the impedance offered for that is a non-Faradaic impedance. Okay, so this is here we are calling it a Faradaic impedance because there is an electron transfer across the electrode-electrolyte interface, which is happening at particular speed, which is governed by the charge transfer resistance offered by that particular electrode-electrolyte interface. Similarly, there is another interface here, so that also will have a similar contribution of there is a capacitive contribution and there is a charge transfer contribution or Faradaic resistance or charge transfer resistance. This can be said in multiple ways: RF or RCT. RCT stands for charge transfer resistance. So this is anode. So there is a charge transfer resistance for the cathode as well. and this is a capacitance for the anode. This is a capacitance for the cathode. So sometimes the reaction happening at one particular electrode may be very fast compared to the other electrode. Therefore, we can assume that the impedance offered by this electrode, okay, is much smaller than the impedance offered by this electrode. Therefore, this quantity can be absorbed into this, and then we can simplify the circuit like this. Okay, this is a circuit for electrode of our interest, okay, which is slower compared to the other electrode. Okay, so in this case, as I said, this is a capacitance associated with this electrode electrolyte interface, and this is a charge transfer resistance associated with the electron transfer that happens at this interface, and this is a solution cum contact resistance, which also has the other electrodes tiny resistive contribution into this. Okay, any questions so far? If not, I will proceed.
Sir, I have a question, like why does impedance comes, and does it affects the cell performance due to this impedance?
Any cell you assemble which can be modeled as if it has some impedance. Okay.
Okay.
Why it has to be modeled that way? Because cell doesn't know there is an impedance, but we are modeling and understanding the cell that way. Okay. So, and why we like it? Because all the electrical techniques can be done without opening the cell from outside. Therefore, we are liking these techniques so much than spectroscopy and other techniques. So, if you look at here, when you do a reaction, for example, hydrogen comes to the anode, becomes H+. At that time, what it does, it gives the electron to the electrode, right?
Yes.
But in the electrode-electrolyte interface, there is something called double layer. Double layer means that the electrode will have, suppose if it has positive charge, then the negative ions from the solution will align here, correct?
Yes, yes.
Then because of this charge separation, you have a potential across this interface. Okay. So when the hydrogen actually enters this region, it will see this potential. Therefore, the electron from the hydrogen is extracted into the electrode. This is a mechanism by which, general mechanism by which, the electron transfer happens. So the magnitude of this potential drop and the structure of this double layer decides how easy the electron can go from hydrogen to electrode.
Yes. Yes.
Therefore, there is a resistance. It is not a free flow. Hydrogen comes just like that, gives is not possible because there are some ions already sitting here. Hydrogen has to displace that ion, then get attached to the electrode, then electron transfer has to happen. There is a process.
Yes.
Therefore, this resistance comes there.
Understood, sir. Understood.
Whereas if you take a double layer capacitance, in a double layer capacitance, what happens? You have a dielectric here. Dielectric only, changes its, polarity depending upon the field, correct? So if you have a negative field this side, the dielectric oriented this way, correct?
Yes.
But here what will happen? You have moved the electron from here to here by some force, correct? But the electron was never crossing this. And you took electron which were metal here. You never took electron from here. You only took electron in the metal and moved it there. Okay. And this is a faster process, but this is very limited. You cannot keep on moving electron like that because the separation of charge creates a field which will oppose what you are doing. Correct?
Yes, yes, yes.
So therefore, the amount of charge you can store by this process of moving electron from one plate to other plate is limited. That's why capacitors are power device, not energy device, because it has a limited amount of electron you can move with the capacitor. Okay. Whereas if you are able to do the reaction, that means you are able to shuttle the electron at the interface, then you can keep on doing that. Then it becomes an energy device, right? It's like keep filling your tank. Depending upon the capacity of tank, you can fill any amount you want. Yeah. So therefore I model this. But your electrolyte can also act like a dielectric. Therefore, every electrode is a combination of a capacitor come a resistor. And then you have a flow of ions in the solution have a resistance. Therefore, you have a solution resistance. So this is a typical Randall's circuit one would use to characterize an electrode-electrolyte interface. Did I answer your question?
Yes, sir. Sure. Yes. Thank you.
So now, what we are going to do, we are going to use impedance spectroscopy. Let me talk a few seconds about impedance spectroscopy. So now, if you have a reaction going, suppose you have an anode and a cathode. So you apply, if you are doing electrolysis, you will use a power source, or if you are having a galvanic cell like fuel cell, then you will have a resistor only. Then it will be like this. There you vary the resistor, then you will get a different amount of current going through the circuit. Here you can vary voltage that is applied, you can conduct the electrolysis at different rate. Okay, whatever it is, there's an electron flowing and there is a potential generated across the terminal, right? Now, suppose I'm applying some DC potential to this circuit. So let me say the DC potential is here, VDC. And what I'm going to do, on top of this DC potential, I am going to apply a small amount of AC potential. Okay, small amount of AC potential. So I'm going to do like this. Okay, like a sinusoidal fashion. So the potential applied, we applied going to be something like some kind of VAC and then sine omega t. Okay, so this amplitude of this is my VAC or delta, we can say very small amount. So delta VAC, and it is done in a sine wave fashion, and omega t is omega is in radians per second. So this sine omega t is the fashion by which we are changing. So this is the applied potential. What is the applied potential? Applied potential, actually, it is this is the only the sine wave part. So your applied potential will be VDC times plus this quantity. Okay. Sometimes this quantity will be positive quantity, sometimes a negative quantity, as here. Okay. Therefore, the value of your potential at the terminal keeps changing, going up, down, going up, down, going up, down. Correct. So suppose I apply one cycle of this potential in 1 second. That is called 1 hertz. Suppose I apply this in 0.1 seconds. Okay, that means 1 cycle in 0.1 seconds is 10 hertz. So what it means, I can apply this tiny potential perturbation at different frequencies. I can do it at 1 hertz, I can do it at 10 hertz, 100 hertz. Depending upon how many cycles I complete in 1 second, I can change the frequency. Okay, so the omega is related to the frequency by this relation 2 pi f, where this is in hertz, this is in radians per second. Okay, so now let us take a simple resistor. In that resistor, I am going to apply this frequency generator. So then my voltage that is applied across that will be delta VAC sine omega t. And it is only simple resistor. Resistors, whenever voltage rises across the resistor, current will flow. Whenever the voltage drop across the resistor, current will reduce. That is by the formula of Ohm's law. Okay. Then your current will also follow the same thing. Only thing is, current will be voltage time by R. R is the resistance of this circuit. So this R times sine omega t. So if this is your voltage waveform, this is your current waveform. So your current waveform, if you look at it, this is in phase with your voltage waveform. Whenever voltage rise, current rise. Whenever voltage drops, current drops. So that means the frequency at which you are applying voltage perturbation and the frequency at which you see current perturbation is the same. Okay. So that means the resistance of this circuit is a delta V by delta I. Okay, this is a DC component and this is also the DC current component that comes. That only tells you what is the impedance of this resistor. Suppose I have a capacitor. So for capacitor, I do the same thing. V is equal to delta VAC sine omega t. Now we know capacitance is Q by V, which is I by dV by dt. Okay. So then I is equal to capacitance times dV by dt. Capacitance times what is dV? Delta VAC cos omega t into omega. Correct? So it becomes C omega delta VAC cos omega t or C omega delta VAC sin omega t plus 90. Correct? So what happens? So when you have voltage versus time plot, so this is how you are changing the voltage. But what happened to the current? Current is maximum when this is current, right? Imagine when t is equal to 0. At t is equal to 0, I'm here. So it becomes sin 90. Sin 90 is 1. Whereas if you do it for voltage waveform, when t is equal to 0, voltage is 0. So whenever there is what you call whenever the voltage is low, current will be high. Whenever voltage is high, current is low, right? So this voltage is low, current will be high. And whenever the voltage is high, current is low again. Okay. So you see there is a 90-degree shift in the waveform between the voltage and current when you have pure capacitor in the circuit. But the circuit we wanted to model is a combination of capacitor and the resistor. So if you add the impedance of this guy and the impedance of this guy, because the resistance of a capacitor is called as a impedance. That's why the word impedance came, because not only a resistor in a circuit, we have capacitor and inductor also. Therefore, this entire resistance of this is called impedance. Okay. So now this, how will you do this? So we know for a simple resistor, impedance of a simple resistor is just resistance. Whereas the impedance of a capacitor is minus J by omega C. What is J? J is a complex number, root minus 1. And omega is the radians per second, and C is the capacitance that you have seen. So this is the impedance of your capacitor. Now these two impedance of this guy and impedance of this guy are in parallel. So what you have to do, you have to add them. You know, how will you do that? 1 by Z total, okay, equal to 1 by that resistance, and we call that as a charge transfer resistance or Faraday resistance. Okay, so I am doing it now only for this circuit. I am neglecting the RS here. Okay, and minus what happens? Omega C DL double layer capacitance by J. Correct? Okay. So by J, this is how you need to add them, because you need to, how did I get this? I get it like this: 1 by resistance of this plus 1 by minus J by omega C. Then it goes up, this goes up. That's how I get this. Okay. So this is going to be my total impedance. But you should see one thing. In case of resistor, where is the resistors here? If you look at it, both are sine. So my impedance Z equal to delta V by delta I. So that means V by I. And V by I, if you do, everything get cancelled. You can see. So what you get is only R. Okay. So whereas if you do the same thing for this guy, impedance for a capacitor. So you do the delta V by delta I. Correct, no? So delta V by delta I, if you do, what is delta V? Delta V was some delta V sine omega t. And what was the delta I? Delta I was C times omega times delta V times sine omega t plus 90. Correct? So if you look at it, this is a function of, if you see, these are all some constant, we don't worry about it. But you can see the impedance now becomes a function of frequency. Whereas in case of a resistor, it was not a function of frequency. Whereas the impedance of a capacitor, if you see, that becomes a function of frequency. That's what I wanted to highlight here. The total impedance now is a function of frequency. Why it is function of frequency? There's no problem with the resistor, but there's a problem with the capacitor. It is a function of frequency. Okay, the resistance of a capacitor is not same at each frequency. With change in frequency, it will keep changing, right? So now, if you look at this, and now we'll go to the next thing. If you look at it, the total impedance, I can write it like this as 1 by R plus I omega C. Okay, that is nothing but, if you multiply by the complex conjugate on both sides, you will end up getting the following: R by 1 plus omega squared R squared C squared minus, okay, I omega R squared C by 1 plus omega squared R squared C squared. This is what you will get. So you have a real part, and because I means J, so you have got an imaginary part. Okay, you have got an imaginary part, real part. So we call it as a real part of the impedance minus imaginary part of the impedance. Okay, this is how we represent like a complex number, the total impedance of the circuit. Suppose if you have a what do you call the solution resistance? The solution resistance will get added to the real part of this. Okay, so the then if you look at it, so your total impedance for this circuit would be something like this, equal to solution resistance plus RF, which is the Faraday resistance, plus 1 by omega RC square minus J omega C RF by 1 plus omega C R square RF square. Okay. So this is how your total impedance will look like when you have a solution resistance combined with that. Now what we can do, we can plot the real impedance, real part of the impedance and the imaginary part of the impedance. Okay, this is a real part, this is the imaginary part. We can plot these things. So these are all in the unit of ohms. Okay, if we plot it, so you will have like this, a semicircle. Okay, so what is this? Let us again redraw the circuit. So this is my RF, okay, and this is my capacitor, and this is my solution resistance. So what I am going to do, I am going to take a cell and I apply a potential, and there is a current that is flowing. When the DC potential is applied, I have applied an AC frequency on top of that, and I am measuring the impedance of the circuit. So that means I am measuring these components, RS, RF, C, and all those things. So when I do that, I plot the real value here, the imaginary value here for each frequency. This is a high frequency side. Okay, from the high frequency side, I am going to low frequency. This is a low frequency. This may be in millihertz. This side may be millihertz. Okay, and this will be 1 megahertz or something like that. 1 megahertz or something like that. So from high frequency to low frequency, I am going and keep on measuring the impedance. Ideally, if you have only the resistor, what will happen? You will have only one point correspond to that resistance. Whatever may be the frequency, you will have the same. All the points will fall in the same place, irrespective of the frequency. But the moment you have a capacitor in with that impedance of this circuit is not constant. It changes with the frequency. That's what we have seen in the previous relation. So therefore, the impedance starts spreading out like this, and it forms a nice semicircle when you have this RC circuit. And when you have the solution resistance, then impedance starts at a distance from the origin. So this is proportional to RS. So this point is RS, solution resistance. The diameter of this circle is your RF, which is a charge transfer resistance. And this topmost point of the semicircle is equivalent to omega RC equal to 1. So we know what is the RF value. So we substitute RF value, and we know what is the frequency at which we got this point. So we know omega. Then we can calculate what is C from this relation. So this is called Nyquist plot. It's called what? Nyquist plot. That shows what is the value of C, what is the value of RF, what is the value of RS. So like that, we can find out for the circuit what is the impedance at a given DC potential, on top of which you will apply a AC potential. Okay. So this is a circuit. Okay. Now we can do this for a different potential. What I mean, I have this, I have this. What I have done? I have done it at particular DC potential. Imagine I vary this DC potential. What happens? According to the Butler-Ulmer equation or Tafel equation, current is e power alpha NF eta by RT. That means when you change the potential, over potential changing means what? Applied potential is changing, because over potential is nothing but E applied minus the equilibrium potential, right? So when you change over potential, you are changing the applied potential. When you are changing the applied potential, current is changing. When the current is changing, how the current can change in the circuit? Because solution resistance cannot change. So that means the impedance of the circuit is changing. How the impedance of the circuit is changing at a given DC potential? Because this is called charge transfer resistance, right? Or Faraday resistance. This resistance changes. Why it changes? That is what dictated by this equation. This equation says when over potential is changing, current is increasing. When the over potential is increasing, current is increasing. That's what this equation says. That means how this is possible? Only if the resistance, which is correspond to the charge transfer across the interface, should decrease. That means this should be a function of, this RF should be a function of applied potential. Okay. So this is a function of applied potential. That is why when our potential increase, it's equivalent to decreasing the resistance value. Therefore, more current flows in the circuit. Okay. That's how you have to look at it. So this is a function of DC. That means now let us do the impedance plot or Nyquist plot at a different potential of DC potentials. Let's say now I am doing a fuel cell. Fuel cell starting voltage is 1.23. Okay, this is 1.23 volt. This is a current. So as you decrease the potential in this case, that means increase the over potential. Decreasing the cell potential means increasing over potential. As you see, the current is increasing. Correct. Current is keep increasing. So let us do an impedance at this point, 1.21 volt, and we will do an impedance say at around 1 volt. Let us do an impedance say at around 0.8 volt. How it will look like? For all this, for this fuel cell, the electrolyte is same. Okay, the fuel cell electrolyte same. Only thing what we are doing, the potential that we are allowing, or because the fuel cell, no. So you have the resistor. By manipulating the value of the resistance, the voltage across these resistors can vary. This can be 1.21, or it can be 1 volt, or it can be 0.8 volt. That depends on how we are changing this external load or resistor. Okay. Now we need to do impedance at this potential, this potential, this potential. How it will look? Electrolyte is same. That means solution resistance will not change. Then the capacitance may not change much, but there can be still some changes because your electrode interface is not a perfect EDLC capacitor. It is a leaky capacitor, so there can be a change in the capacitance with the potential. And then there is a charge transfer resistance, which is a Faraday resistance. Okay, this is changing with the over potential. You should remember that, right? Or applied DC potential. Now what will happen? We know as we go this way, current is increasing. That means the RF must be decreasing. Okay, then how will you plot that? So this is RS, this is imaginary Z, and this is a real Z. Okay, so this is RS. So I'm going to plot first for 1.21 case. Then what will happen? I will have some particular resistance for the charge transfer across this interface. Say this is what it is. And then now I'm going to 1.0 volt. When I go to 1.0 volt from this polarization curve, we can understand at 1.0 volt, the current is more compared to what is at 1.1 volts. So current is increasing this way. Current is more. That means Faraday resistance or charge transfer resistance should have decreased. Okay. Then you will see if you do the impedance summation, you will see the starting point is same, but the semicircle would have been a smaller one. Okay, because the diameter of the semicircle only tells you what is RF or RCT. That is decreased now. But starting point is not decreased because the solution resistance remains same irrespective of the applied DC potential. Now let's go to the condition of 0.8 volt. What happens here? Current increases further. That means RF should have decreased further. Then how will you show that? You can show it like this. Right now. So this is how your collection of Nyquist plot will look like when you apply different over potential. So this is the over potential increasing direction is this way. Applied potential decreases means over potential increases. This is applied potential. Okay. So now you see with increasing over potential, you see the RCT shortening. Okay. And that you can measure from the impedance. And if you multiply the RF value and the CDL value, that gives you time constant. Suppose imagine I have an electrode in which there are two reactions going on. One case A goes to B. In another case, A goes to say some C. Okay, that means two reactions are possible. In that case, these two reactions may have a two different rate constant. Rate constant means the inverse of the rate constant. Rate constant is what? It's like higher the rate constant, faster the reaction, right? So it can have a two different rate. These two reactions can have two different rate or two different rate constant. That means two different. The inverse of the rate constant will give you in the unit of seconds, right? So because the first order rate constant K is second inverse, so 1 over K is going to be second, right? So that means depending upon the how many rate constant you have, you may have a two different characteristic time. Okay, that's called tau in this case. Okay, the RC tells you the value of tau. That's characteristic time constant. Okay, suppose if you have two processes which are of varying in time constant, then how it will look like? This is your solution resistance. Then you have a capacitor associated with that interface, and you have a resistor or charge transfer resistance for a reaction 1, which is A goes to B. This is for A goes to B. And you may also have parallelly something else is happening. That is, there is another reaction, okay, wherein A goes to C. Further, there is a Faraday resistance, okay, for A goes to C, and you have another Faraday resistance for A goes to B, and there is a different charge transfer, capacitance associated with that. So this is how your equivalent circuit will look like. So you have to calculate the impedance of this entire thing here. Then how it will look in your impedance plot, okay, minus imaginary Z and real Z. If you look at it, so you have a solution resistance, and I have guaranteed you that the time constant tau, that is R times C, okay, R of C. This RFC is for the RF correspond to A goes to C. The serial correspond to A goes to C. Similarly, this tau, you can say tau 1, this is tau 2. This is correspond to A goes to B. And this C correspond to, say, A goes to B. So you have a two distinct time constant. Then what will happen? You may have a two semicircle. Okay, one of them will be correspond to, we don't know which one is what. Further, you need to change the concentration or do some other additional studies to find out which one belong to what. But what we understand from this figure is there are two distinct time constants, because this place also omega r is equal to 1. This place also omega r is equal to 1. So the frequency is different here and the frequency is different here. Definitely this frequency is smaller than this frequency, because this is a high frequency end, this is a low frequency end. And the frequency decreases, then some changes would have happened in RC to make it as 1, right? So definitely these two RCs are not equal. So this clearly tells in a given electrode-electrolyte interface, there are two different reactions that goes on looking at it. What will happen if the time constant is same? The time constant is same, even though your circuit is this, you will still get to only one semicircle. If your time constants are very close to each other, then what will happen? You may have a depressed semicircle. Why? Because this can be deconvoluted into two semicircles like this. Because the time constants are so close to each other, so they overlap and form the one depressed semicircle. So this is we can use as an external tool. So you take a fuel cell pack and you can do an impedance and understand how the impedance, okay, response of your cell is changing with the time. So with the time, what can happen? For example, so this is imaginary Z, this is a real Z. Imagine I got a response on the very first day like this. Okay, very first day I got a response like that. Now after 1 year I am measuring. After 1 year, say this becomes like this. What is my conclusion here? Since the diameter of the semicircle almost is constant, but the starting point has changed. That means in the circuit, this portion is changed. This portion corresponds to what is electrolyte. That means the membrane, that is the ion conducting membrane in the fuel cell, has got into some problem. Therefore, the resistance of that membrane is slightly increased. Therefore, the protons which are moving through the membrane faces trouble. That is reflecting in the impedance spectroscopy. Okay. Suppose differently, suppose some other way it appears. Suppose this is the first day is like this, and I am coming after 1 year and look at it. Then it goes like this, suppose. What it clearly tells, nothing happened to the electrolyte, whereas the charge transfer resistance, which is the diameter of the semicircle, definitely increased. That means the reactions are slowed down at the electrolyte interface in a given potential. Okay, that means the catalyst is losing its surface area, or some corrosion has happened, so the electrode has degraded. Therefore, the rate of the reaction has come down. Hence, the current has come down. Hence, the charge transfer resistance has gone up. These are the conclusions we can make. Okay, so the membrane resistance can also increase if the membrane is not hydrated enough. Generally, in fuel cell membrane, the membrane has to be hydrated. Okay, so what we can do in that case, we can change the relative humidity and we can calculate what is the RS, okay, at each relative humidity. So maybe the RS, say this is a relative humidity plot, this is a relative humidity, and say this is a solution resistance or electrolyte resistance. Suppose solution resistance at some 0, say at 100% relative humidity, say somewhere here, okay, and then I'm keep on decreasing the relative humidity. So this is 0%. Then what can happen? This may be constant for some time, but after that, this may go up like that. So what it means? That means this is the relative humidity below which I cannot operate the cell. Why? My solution resistance going like infinity. Okay, so I need to operate in this region where the relative humidity between 100 to say 70% or something. So in this region only my solution resistance remains low. Otherwise, cell cannot be operated at this very low relative humidity because membrane dries. Therefore, the solution resistance goes up. If in this circuit, even though your charge transfer resistance is good, even though your CDL is good, but if this becomes infinity, then the significance of this is gone. That means the catalyst or electrolyte interface is gone because the electrolyte resistance is gone to infinity. Okay. Therefore, we need to use this impedance to understand the health of the membrane, to understand the electrode electrolyte interface, and understand what kind of, and we have to combine impedance with the other techniques, and understand electrochem. For example, one other technique with which we can do is we can measure the surface area of the electrode by a technique called hydrogen UPD, hydrogen under potential deposition. Okay, under potential deposition. This actually measures the surface area of the platinum electrode, electrochemical surface area of the platinum electrode, which is inside the fuel cell. So we can use this technique in conjunction with our impedance technique and understand what is going on inside the cell without opening it. So this is called non-invasive, non-destructive diagnostic techniques. So this is one of them. Okay, this is how we look at the state of health of fuel cell with the time. Okay, I will stop here. If you have any question, I will be happy to answer.
Thank you, sir. Thank you for your valuable session. So we'll ask the participant that if any query, please raise your hand. We'll unmute you.
The participants are encouraged to ask questions. Actually, I would like to share my gratitude to Professor Kodandaraman for the short notice, and he has agreed to take the session out of his generosity. Especially during the lunchtime, paying a lot of attention in writing on the iPad is not that easy, sir.
Yeah, that's what we do nowadays all the time, because there are a lot of online class.
Yes. Please, there is some question in the chat box, I think. General appreciation. Yes. Tatvam Joshi, sir, you can ask the question. I have unmuted you.
Yes, sir. Sir, I will not take that much time, but sir, there was doubt in how the RF value is related to VDC. I was not getting that properly.
Okay, yeah, I'm not surprised, because it's not that easy in 1 hour to make you understand, but I will try my best again. See, are you understanding this TOEFL equation? Did you understand this part?
Joshi, sir, please respond. I think he said maybe his.
Yeah, I'm not hearing him.
I think he understood, sir. He has given the thumb symbol.
Okay, I cannot see all those things because my screen is full of white boxes.
Yes, sir, yes.
See, now the current and over potential are related by a exponential. So now let us look at the oxidation reaction. There is hydrogen going to H plus electrons. Okay. So for this reaction, when I change over potential, current changes. So in a regular Ohm's law, how will you understand if a resistance, okay, if the voltage is increasing, current will increase because resistance is fixed. Okay. Whereas here, what happens? Resistance is not fixed. Why resistance is not fixed? Because the way you have to look at it, a reaction as a reactant and a product. Okay. The reactant to product, how fast you go from the reactant to product side depends on what is the height of this mountain. Okay. By applying over potential, what you are doing? By applying over potential, you are reducing the height of this mountain. Okay. Therefore, each time you apply a potential or over potential, you are actually reducing the activation energy. Because you are reducing activation energy, current is increasing, not because clear. So therefore, that R value, just like in your Ohm's law, it's not fixed here, because this R value changes. How will you understand this? The way you understand is, I applied over potential, so the mountain height has come down. Therefore, more of reactant has gone to product. Every time something moving from reactant to product, that will show up as a current in your ammeter. Therefore, the resistance now becomes a function of the applied over potential. What resistance? Charge transfer resistance or Faraday resistance. Okay. So therefore, in the circuit, if you look at it, this is your solution resistance. This is just like a Ohm's law. It will not change at all. But whereas this resistance is now a function of over potential or applied potential. Okay. Why it is a function of over potential or applied potential? That is dictated by our TOEFL equation or Butler-Ulmer equation. That tells there is a relation between the current and over potential. Therefore, this happens. Clear?
Yes, sir. We are providing this over potential by external source.
Yeah, over potential can be an external source or internal source. If you are doing electrolysis, you are giving over potential by an external source. If you are doing a fuel cell is supposed to give 1.23 volt, but you may be seeing only 0.8 volt or 0.6 volt. Why? Because that much amount is lost as over potential to drive the current through the cell.
Okay, sir. Got it.
Participants should interact with the speaker.
They must be hungry.
Yes, sir. I repeat again. It's a great learning experience from experienced faculty. So please ask questions. Most of them are budding engineers, budding faculty. So please interact with the speaker. Sir, this I have a question when it, I mean, it's a basic question. What do you mean by this different types of polarizations are there in a fuel cell? When it comes to fuel cell, there are different types of polarizations like concentration polarization, ionic polarization, and then activation. So what is this reverse current, sir? I mean, electron impedance. Sometimes I heard that during the current collector, the electrons may reversely it will flow from cathode to anode instead of anode to cathode. So that does it relate to a polarization thing?
No, the reverse current can happen only during start and stop. Okay. And because again, what may be happening when you are starting, the anode side, there should be purely hydrogen. The cathode side, there should be purely oxygen, correct?
Yes.
But when you are starting the cell, what can happen is some oxygen might have entered this side. Okay. So the oxygen in the anode may be undergoing reduction. Okay. For oxygen to undergo reduction, we need electron, correct?
Yes.
Where did the electron come from? This side we have only oxygen.
Right, sir.
The electron comes from this carbon. What is this carbon, the cathode? Because we are having a platinum catalyst coated on carbon, correct?
Yes.
So that carbon will undergo oxidation. Okay. Imagine something like that. If that happens, this electron is what is reducing this oxygen at the anode side.
Okay.
Okay. But this will not happen in the normal operation of the fuel cell.
Right.
This will happen when you are starting the fuel cell.
Yes, sir. Yes.
Means when you are starting the fuel cell, you should ensure you are purging hydrogen gas enough before starting the cell.
Correct.
If you are not doing that, what will happen? This reversal can happen. This reversal will only go for a momentary period, maybe a few seconds. But it is degrading the carbon, converting that to carbon dioxide. So you see carbon plus oxygen will become carbon dioxide, correct? Basically what happened? Carbon has given 4 electrons. And that 4 electron combined with this oxygen produces carbon dioxide, correct?
Yes.
So basically this reaction has to be stopped. For that only they are giving some operating, the manual, they would have given you some procedure to follow to start and stop.
Correct.
Okay. So this is not related to normal operation of cell. But the polarization question that you asked, where we have the voltage versus current, you see the curve is like that. I told you this initial loss is an activation loss.
Yes.
Or this is my equilibrium potential. Okay.
Yes, understood.
And this is my applied potential. So the difference between the equilibrium potential and applied potential is the over potential. But over potential has a different types: activation over potential, ohmic over potential, concentration over potential. All of them will play simultaneously. But if you look at in this region, there's a sudden drop. That is due to the activation over potential. That's because you need to overcome an activation barrier for any reaction, right? So some energy is utilized for that.
Yes.
So that is called activation over potential. And then the current has to flow through the external circuit. And also ion has to flow through the internal circuit. So there is an impedance for the flow of charges. So that we call it as a ohmic over potential. That is governed by the Ohm's law.
Okay.
Yeah. And then we have concentration over potential. See, for the reaction to happen, there should be a reactant, correct?
Correct.
Suppose you are sitting here, it's a very high current density. Very high current density, what should happen? Your flow of hydrogen towards anode also should be high, correct? Similarly, flow of oxygen towards cathode also should be high. So that means the mass transport of hydrogen and oxygen towards the respective electrode should be high. If it is not, then what will happen? The electrode will convert hydrogen to proton only whenever hydrogen comes. Other times, the electrode will simply sleep. So the average current will fall down then. So that is this region. In this region, you are not able to send hydrogen at the speed required.
Yes, sir. Yes.
So there is over potential due to that. But you don't think here only a concentration over potential there. It might have started here itself, but the contribution may be low. But as you go more and more current, this will increase like anything. Yeah.
Yes, I got the point.
Yeah.
Again, I think Tatvam Joshi.
Yeah, please.
Sir, please.
Yes, sir. Let's say, sir, for a fuel cell of 1 kilowatt capacity, sir, what will be the current range for working properly?
That is depends on the design of your cell. Because I can make a cell with this big electrode, or I can make a cell with this big electrode. Okay, I can reach 1 kilowatt by stacking different numbers of cell here and a different number of cell here, correct? So typically we will call it by aerial current density. So roughly about 100 to 200 milliampere per centimeter square is the kind of current is recommended, because that stays in this region somewhere here. Okay, this is a voltage versus current curve, polarization curve. So suppose if I have a 100 centimeter squared electrode, that means a 200 milliampere per centimeter squared into 100 centimeter squared is about 20 ampere, correct?
Yes, sir.
So 20 ampere will be the current that is flowing through this cell, if this is the current density and this is the area of the each cell.
Okay, sir. Got it.
Any other participant? Participants have to can introduce themselves when they ask the question. I think many of them are just waiting for lunchtime, maybe.
It's difficult online now. It's very difficult.
Yes, sir. Yes, sir. Actually, next time we would plan for the offline.
No problem.
Thank you very much, Professor.
Sure. Thank you.
We are very much delighted to have you here in this short-term training program. I extend my gratitude, sir, for you. Thank you so much, sir. Thank you.
Thank you. Thank you, sir.
Thank you very much.
Bye.
Thanks.
Bye, sir.
Participants, please fill the feedback forms. If it says that it's already responded, that means the previous links are also the same links. Please don't worry. Yes, I'm sharing again. Please fill the feedback links.
Please fill it. We shared already. It was like a previous link and this link is also same. So if you fill, there is no issue.
Yeah.
We'll give maximum